Nitrogen dioxide decomposes at high temperature. 2NO2 gas, 2NO plus O2. Delta H is plus 113 kilojoules per mole to power minus 1. A 0.317 mole sample of nitrogen dioxide is placed in a sealed flask and heated at constant temperature until equilibrium is reached. At equilibrium, the flask contains 0.121 moles of oxygen. Calculate the mole fraction of each substance at equilibrium. 3 marks. And then we've got 4.2. That looks pretty easy. 4.3. That also looks pretty easy. And then 4.4, 4.5. Okay, so 4.1. The best approach that I would do is draw out the table. We've got NO2, because we're trying to find a mole fraction of NO2, not 2NO2. We've got NO and we've got O2. So the M stands for moles, C stands for change in moles, E stands for equilibrium moles. And then in this case we need more than that. And then we get the mole fraction, then we get the partial pressure, and then we can find out Kp, or the total pressure. So NO2, then we can find out Kp of partial pressure. A 0.137 sample of nitrogen dioxide, 0.317 total equilibrium is reached. At equilibrium, the flask contains 0.120 of oxygen. Therefore, equilibrium moles is 0.102. 0.120, we're going to assume is 0 at the beginning. So the change, 0.120. We're going to assume there's 0 here at the beginning. We're going to also add 0.120. However, because there's 2 here and there's basically a 1 here, 2 to 1 ratio, we're going to times that by 2, and therefore it's going to be 0.240. And because we're adding on this side, therefore we're going to be subtracting on this side, so it should be minus 0.120, also times by 2, because we've got a 2 there, times by 2, and that will give us 0.317 minus 0.120 times by 2, 0.077. But we want to find out mole fraction. So the mole fraction, firstly, let's find out the total moles at equilibrium. 0.077 plus 0.240 plus 0.120, 0.437. 0.437. Therefore, mole fraction of NO2 is going to be 0.077 over 0.437. 0.077 over 0.437. 77 over 437. Which is 0.176. Because what does it want it to? Yeah, 0.176, 0.176. NO is going to be 0.240 divided by 0.437, 0.549. And the final one, 0.120 divided by 0.437, 0.275. 0.176, 0.549, 0.275 for 3 marks. Part B says, 4.2 says, the total pressure in the flask in question 4.1 is 120 kilopascals at equilibrium. Calculate the partial pressure of NO2. And then this bit is when, if you weren't able to answer question 4.1, they'll still give you a mark if you know how to calculate partial pressure. But we calculated it, correct. I calculated correctly. So the partial pressure of NO2 is going to be partial. Remember this formula: partial pressure is equal to mole fraction times by total pressure. So in this case, we're trying to find of NO2. What is the mole fraction of NO2? 0.176. 0.176 times by total pressure 120 in kilopascals. We don't convert into pascals, and we get 21.12. Does it say to any significant figures? No. 21.12 kilopascals. So we'll just say three significant figures. 21.1 significant figures. 21.1 kilopascals. Actually, just forget it. We'll just leave it as that. 21.1 kilopascals. 4.3 shows mole fractions of three gases in a different equilibrium mixture. For this equilibrium mixture, Kp is that. Give an expression for Kp. So let's do that because that should be pretty simple. Give an expression for Kp. Well, it's going to be products of reactants. So it's going to be partial pressure of actually, let's just do it again. Kp, in this case we'll just use P is equal to P of NO2 squared, 2 moles of NO2 times by O2, yeah, over P of, no, that should be NO squared over NO2 squared. So we've done that. We know the Kp is that. We want to find the total pressure in kilopascals in the flask. How would we do that? How would we do that? Well, remember the formula I just said before. Partial pressure is equal to mole fraction times by total pressure. We're trying to find the total pressure. So surely it's going to be partial pressure divided by mole fraction. So we're going to need to know the mole fractions of NO2, NO, and O2. And what we can do is, because we know Kp is equal to this, what we're trying to find is the total pressure. What we can say is that total pressure rearrange it, we get total pressure is Kp times by mole fraction of NO2 squared over mole fraction of NO squared times by mole fraction of O2. And now we just substitute the values in. So Kp is 59.7 times by mole fraction of NO2 squared, which is what? Of NO2 squared. Actually, no, we're not going to use that. We're going to use these values. This is a separate one. So 0.310 squared over mole fraction of NO squared 0.460 squared times by 0.230, and we get 118 or 117.9. Yeah, 117.9 kilopascals. Well, if the equilibrium mixture is in a smaller volume, well then the equilibrium yield of oxygen is going to decrease. Smaller volume, so the effect on the yield of oxygen was also going to decrease because oxygen is part of the equilibrium mixture and you're compressing in a smaller volume, so oxygen, the yield has got to decrease. And then also deduce the effect on the value of Kp, that's going to be no effect. Remember, for Kp, same as with Kc, only temperature can affect Kp, can affect, well, I should say yield or equilibrium yield, but you get the point. Equilibrium mixture question 4.3 is allowed to reach equilibrium at a lower temperature. Explain why the equilibrium yield of oxygen decreases. Question 4.3. So at a lower temperature, well, we know delta H is positive, 113. So that tells me the forward reaction is endothermic. Therefore, the reverse reaction is exothermic. And if we decrease the temperature at lower temperature, well, which side is it going to shift to? Well, if we decrease the temperature, it's going to shift to the left hand side to increase the temperature, exothermic side. It's going to shift to the left hand side to increase temperature. So therefore the equilibrium yield of NO2 will increase, and equilibrium yield of oxygen will decrease. So what would we start off? Reaction is endothermic, delta H positive, exothermic in backwards, get reverse direction, hence equilibrium shifts to the left hand side to oppose decrease in temperature to raise the temperature. And that is how you'd explain it. Reaction is endothermic, exothermic in backwards, that's reverse direction, but this bit is what you really need. Reaction endothermic, hence equilibrium shift to left hand side to oppose a decrease in temperature, hence to raise the temperature. That is the end of question 4.